Hello, it's everyone. My name is Christos Karras. Today I will be presenting the paper entitled Three Data Structures and Efficient Indexing Techniques for Big Data Management, a comprehensive study. This is a joint work with Dimitrios, Samoladas, my brother and colleague Aristeidis, Karras, Dr. Leonidas, Theodorakopoulos, and the Professor Spyros, Sioutas. Starting with the introduction and the motivation behind this work, in the past decade there has been a significant increase in the amount of information and data that is being produced. This is either by IoT sensors, by multimodal techniques, deep learning, machine learning, and so on. So as a result of this matter, there has been an increasing interest in order to develop high-performance systems and techniques that can effectively handle such data. So such systems are able to provide responses to queries across terabytes of data in just a couple of seconds. And in particular, in this work, we survey the emerging tree data structures and we present some index mechanisms to assess their matter in the sector of big data management. And we also perform some experiments based on the centralized and decentralized variants of particular trees. Starting off with the overview and the indexes. The indexes that we will talk about is the B plus tree, the QuadTree, the KD tree, and more. And we will also go through their distributed implementation based on third-party works. We also perform some experiments on operations at them. But first, let's talk briefly about indexes. Indexes are structures that arose out of the necessity to look up information stored in databases quickly. So records that belong to a given range or generally satisfy a certain criterion, we would have to access the records one by one and check if they meet the certain conditions that we set. For a database of n elements, this would require O(n) time, which is unsuitable on the huge databases that we have nowadays. Therefore, indexes are structures that can improve the search time, and in order to achieve the improvement, these sacrifice space and time rights to the storage in order to maintain the structure, but we have fast lookup times. Therefore, choosing the right index for the task we want to perform is a major part of the whole process, as it can lead to time complexities on searches from O log n to O(1). Starting with the distributed version of the B plus tree, initially we construct the tree as a whole and we store the tree in a HBase table, where each row of it represents a node of the tree using a single MapReduce task. Therefore, we have an arbitrary row key and the columns we have information about the node, such that the keys show the following nodes, the range of the keys covered by the specific node we'll look on. This version receives the data from a dataset using the mapper, and it turns into an appropriate key value pair format. After the records have been constructed, these are passed to a custom partitioner in order to divide the data uniformly throughout the reducers. And in the reduction step of the MapReduce, local B plus trees are generated, which are subsequently connected in order to form the global tree. Here we have two nodes inside the reducer, the current that we look on and the next node. Each pair that enters the reducer is added to the leaf that is currently being constructed, and if this node is full, a new leaf is produced and the enter pair is added into a buffer. Next we have the QuadTree, where QuadTree is a reasonably basic geographical data indexing approach, as we can see on this graphical representation, where each node in the QuadTree represents a given box that covers a portion of the data which is being indexed, with the root node representing the whole region. Each node is either a leaf which includes one or more points in the space and no children, or an internal node which has precisely 4 children, one for each quadrant, resulting from a splitting of the node's space into two vertical axes. These quadrants coming up become new leaf nodes, whereas the node that was splitted becomes an internal node. You have the internal structure of the QuadTree, and the components of the former node are then relocated to their respective quadrants, those tiny regions here. After inserting many items, the resulting tree structure becomes this. This is the whole QuadTree, and these are the quadrants of the QuadTree. Next, we have the KD tree, which one we survey in the paper. And the KD tree is a tree structure where it represents points in the k-dimensional space. It is quite similar to the QuadTree, but its implementation is quite different. In this structure, each internal node divides the space into two parts. On the right side of the node, where it represents the right part, and the left side represents the left part. So this split does not necessarily take place in the middle of the space, as it was on the QuadTree, but at some point chosen so that as much as possible there's an equal distribution of the remaining points of the space of the two parts. So we'll look on the right hand side and on the left hand side. We want to have an equal distribution of the remaining points. Next, we have the distributed KD tree index and the distributed version of the QuadTree, where these distributed index are based on the H base, and these are named MD base records. So this system is intended to address the need for massive input of new data and the real-time spatial query response, which are required by the location-based services, as known as LSBs. And within the system, the authors of the distributed versions implement two data structures, the KD tree and the QuadTree, as we already said, which are stored according to the key value per data model. So in a key value database, generally objects are stored, are ordered by a key and partitioned by the range of the key space. So such, we have a Z order as shown here, where, for example, for the subspace 0101, the Z order is 0011, where this follows from the surrounding space, which is named as 00, and the subspace itself 0101, which has the name 11. So if we join the two names, we get the Z order 0011 of the subspace 0101. Next, we follow the experimental results in this slide. And the data utilized in the experiments, which was created via simulating massive datasets using a data generator in order to evaluate the distributed index of the B plus tree. Simulated dataset is 1 gigabyte as per size, and it includes 9 million records. Initially, the file is stored in HDFS before we construct the index and we start off with the experiments. And the building time of the centralized B plus tree is much longer as the time of the distributed B plus tree index construction. And this is because the distributed version uses the MapReduce in order to quickly and parallel construct the tree rather than the centralized approach. The times appear in seconds, and as you can see, the centralized B plus tree took 5 times longer than the distributed B plus tree index creation. Next, we go through range queries on the B plus tree, where the range query performance of the centralized and the distributed B plus tree is evaluated. And for the experiments, we use 100 random range queries executed on 300 megabytes on the decentralized tree and 1 gigabyte size of the dataset in the distributed tree. So we do that in order to look whether this would affect the performance. Although the centralized tree dealt with less data, 1/3, than the distributed, which dealt with 1 gigabyte dataset, superior performance is one of the distributed B plus tree. As you can see here, it is faster. And in order to assess whether the distributed B plus tree could further be improved, we use the technique of H-space, which is known as the pre-warm, and this further improved the time for the range queries, even more from the distributed B plus tree without the optimization. So that's quite surprisingly. Moving on to the index experiments and the operations of insert and other basic operations, we do the experiments on the Amazon EC2 cluster, ranging in size from 4 to 16 nodes, where each node has 4 virtual cores, 16 gigabytes of memory, 10.6 terabytes of hard disk, and we use the 64-bit Linux operating system. We have the first measurements where we basically do the insert operation on some models. And in order to simulate the load here, we use load generators that produce basically 10,000 inputs per second, and the number is varied from 0 to 64. So the best performance is using the Z-order technique, the highlighted blue technique, across all experiments for 4 nodes. But basically, for 4 nodes, the KD3 was slightly better, but as we increase the nodes, the Z-order technique, and especially the TBB technique, which is known as table per bucket, is quite better in terms of performance than the other techniques. And as we increase even more the nodes here with 16 nodes, we can see that the Z-order technique has better performance. And we presume that if we increase the nodes even more, the Z-order techniques would scale even better. Moving on to more experiments, we test the response times of selectivity for various models for the KD3s and QuadTrees. So as we can see from the figure on the left-hand side, the best times are for the TBB technique, table per bucket, for the KD3. As you can see here. Basically here, the KD3, the record per bucket was better, but still the more stable response time as log scale response time is the TBB for the KD3, except for the 0.01 case. The times on the left hand side, as we said, are log scaled, and we also assess the number of the nearest neighbors on the right hand side, where the best results are for the TBB technique for the QuadTree. As you can see here, and just on this case, the TBB for the KD3 was faster to look up for nearest neighbors. But generally, the QuadTree is better. This would have have interest to increase even more the numbers in order to look whether the QuadTree would overtake across all experiments. And in conclusion, some remarks and some more about this work. In this work, we have surveyed the P plus 3, the KD3, R3, QuadTree, and more. We cannot cover all of them in the presentation of this paper, but we have covered them in the paper. And we have highlighted the basic insert operation, range search, distributed versions, and more. We have presented some experiments for indexes on most structures, and we can conclude that the KD3 is the best among the others in most experiments. And as per the nearest neighbor search, QuadTree appears to be the fastest structure, but as the data increases, as we said in the previous slide, KD3 overtakes. Future work could cover more state-of-the-art data structures, including the LSM3, X3, and the AX3. And lastly, the experiments could cover more than one type of dataset types, temporal, spatiotemporal, multidimensional, and so on, in order to find the most suitable structure per given use case. That was all. Thanks for your attention, and if you have any questions, I will be happy to answer. Thank you.